Hey everyone! Welcome back to the Flesh Tools series for side effects Project GROT. In the previous chapter, we wrapped up our Flesh Cluster tool and played around with it inside of Unreal. It did an amazing job of adding some disgusting detail to our scene, but it left me longing for more. Perhaps a standalone tool we could use to cover certain areas in Flesh as we see fit. So in this chapter I will show you how we can repurpose parts of our existing tools to quickly create a new standalone Flesh Webs tool that will help our artists to add a final layer of polish to our scene. Let's get into Houdini! Alright, here we are one last time in our Houdini scene, and if you're wondering why I'm still looking at the Flesh clusters, that's just because I thought, because I want to take some of the tech that is inside of the Flesh clusters, I'm just gonna leave them here for when I want to jump into the tool to copy some stuff over. So a little backstory to these Flesh webs. When we were nearing the deadline of our project, we felt like there was still something missing, this like final layer of polish on our scene, especially near the ruins and near the cave entrance where the camera pans in. And we were thinking, the Flesh is so cool on the ruins and on the clusters, why can't we have it be its own standalone tool? And then it kind of hit me that, wait, I already have everything I need. Why try and reinvent the wheel? And so it took me like 1 or 2 days to do the whole thing by ripping out parts of the ruins Flesh and the Flesh clusters, and then we had what we dubbed the Flesh webs because of their cobweb-like look to them. And in the course of this tutorial series, I wanted to give the Flesh webs the same kind of treatment that I've given the clusters and the ruins. So the obvious place where I could improve it would be the simulation, the muscle tension tech. Why don't I just copy it over from the Flesh clusters? And it turned out it looked even better than I had imagined. Well, enough talking about it, why don't we just do it? So what I'm gonna do is I'm just gonna take this environment that we have already and I'm gonna move it over here, and just like with the previous tools that we've been making, I'm gonna make some null nodes to tell us what this is gonna be later on. Collision. The second one is our influence mesh. And the way that this tool is gonna work is a little bit different. We are gonna do a half and half, where we are gonna use the cool Flesh simulation tech from the clusters, and I'm gonna use what we were doing for the ruins, where we just scatter a bunch of points and then connect them and then remove the intersections, but then we simulate it in the same way that we did with the clusters. And the way that we get these scattered points is by what I've prepared here, this influence mesh. For instance, we can use a sphere, or it can be any other object. It could also be a spline, but with a sphere I think it's just easy to understand. Then I'm gonna get a mask from geometry node, and I'm gonna wire up the influence mesh in the right input and the collision in the left input. And then let's visualize this mask attribute. I think it becomes immediately apparent what I'm doing here. So this is just another way that we can create these mask attributes that we've been working so much with during both of these tutorials. Whereas before we have painted it, or we were generating it from ambient occlusion or from noise. This is another way that we can create this attribute by proximity to another object. And if I go over to my mask from geometry, we can increase the radius to basically shift the threshold of this distance. And this can be a very useful parameter to expose, because basically what this radius is gonna define is where the Flesh is allowed to grow. So I don't know, maybe until the light blue circle here. So I'm gonna set this to maybe like 4 for now, and then I'm gonna get a scatter node and plug that in. Then we're gonna switch to density scale, and density attribute I'm gonna type in mask. And just for clarity's sake, I'm gonna increase the density scale a bit. But there is something I wanna address before we move on, and that is how this mask from geometry works. Basically what we are doing is that this color, this mask attribute, is being generated per point. And as you can see on my nicely subdivided grid, This makes for a very smooth gradient, but on these pyramids, it looks like it's missing a bit of information. And even though it's gonna probably work, we don't know that we're always gonna get such a nicely chopped up mesh, right? So let's just see what would happen if, I don't know, what if there are no subdivisions at all, right? So let me just go 2 and 2. What's gonna happen now? Well, exactly. We're not gonna get any mask attribute because there's no vertex to hold on to store this information. So how can we guarantee that there's a base level density of points that we can store the mask attribute in? It might not be the most elegant solution, but what I thought could work is that we simply just cut it up. So let's get a divide node here. And I'm gonna disable all this triangulation stuff. And what I'm gonna do is I'm gonna go over here to breaker polygons. And what this is gonna do is that it's just gonna chop everything up into cubes. And I'm saying cubes because you can see that if I look at it from the side, that this square-shaped chopping pattern is continuing. You know, if I would rotate my grid, you would see that it would keep generating these lines in all axes. And if I look at my mask from geometry, we can see that now we get this smooth gradient again. With this little trick, we basically just guaranteed that whatever comes in, no matter how low poly it is, it doesn't care, and it's still gonna generate a relatively smooth gradient. It doesn't really matter what we do to the geometry because after the scatter we're gonna discard the geometry anyway. I'd be happy to know about a different approach. Feel free to drop it into the comments to let people know. I'm just gonna go with this one. Okay, what do we do now? Well, if you followed my runes tutorial series, you should probably know what's gonna come next, and that is we are first gonna get the enumerate node to store a point attribute, for instance the PT ID. I mean, we can call it whatever, but I'm just going to call it PTID. Or by the way, just to mix it up, I can also show you how we can do this with an attribute wrangle. We can just say, because it's a string attribute, I'm going to say s at, and then PTID equals, and then we can say at PTNum. But it's going to fail because PTNum, or the point number, is an integer, so we first need to convert it to a string, and there's this function called etoa that turns an integer into a string, and now we also have it. So, you know, just a different way to go about doing this. And then I'm gonna get the connect adjacent pieces node, and I'm gonna type PTID. And here we go. Now we're just gonna go again, set max and min radius. So something like between 0.5 meter or maybe 1 meter. And what's kind of curious is that you can see that even though we have this abundance of points, our connect adjacent pieces node is only giving us this weird outer circle, but not connecting to the rest. And that is because of the max search points parameter. So if we increase that, we can see that now we are getting more, and that has to do because basically what this number defines is based on our criteria that we set, you know, minimum distance, maximum distance, which angle, how many connections, all this kind of stuff. It's gonna try to find a viable connection, and then it's gonna move on. But what that means is that even if it tried but didn't find one, that also counts as a search point. If you wanna find all the points, you need to increase it to something higher. But as you can see on my footage also, it's gonna slow down immensely as I do this. So, you know, do this at your own risk. Let me close this again. And then we're already at the point where we want to simulate these splines. That's why I kept these nodes here, so I can jump inside. And then I'm just gonna get, let's see, from the null node to my time shift. I get that. Copy that here. Okay, let's see. And what we should be aware of is that some of the nodes have some parameters because we previously set it up in the HDA. So I'm just gonna delete these channels and just type a placeholder value for now. By the way, and the reason why I called it PTID is because in our flash clusters, we also use this PTID attribute, for instance, to define the connectivity. Let's see what's going on. I'm gonna get a merge node and just gonna wire this up. Get this, and the influence mesh. Okay. Yeah. This looks pretty cool already. Oh yeah, and I'm just gonna add back the detail from our grid so that it looks a bit more interesting. Oh yeah, and it's cool to see how it adapts, right? Like that on the fly, all the flesh is just doing its thing. I really love these parts here. That's so cool. But let's address these intersections here. We don't want those. So the next step is gonna be to solve that. So I'm gonna get a group node, call it intersections points, keep in bounding regions, bounding object. Of course, we need to supply a bounding object. So I'm gonna get our collision. Then we're gonna expand the group to make sure that if even one point intersects, we get rid of the entire thing. All right, then we're gonna blast it. Alright, and I mean it's a bit radical. Like you can see the difference between these two. So it is a bit wasteful, unfortunately, but we can also make this an optional feature if we want to. But now we only have the viable connections left. And then we need to, of course, make sure to allow for more search points. Yeah, I think with something like this, we can get pretty far. All right, I'm just gonna move this over here so it's a bit more clear that this is separate from the other tool. So one feature I liked in the original tool was what I called the hook depth, because as you can see right now, our splines are gently just kind of laying right on top of the model. But what would be cool is if they were kind of trying to enter the rocks or whatever they're on. It makes it feel a bit more aggressive and interconnected. And so what I thought I could do maybe is that we maybe sample the normal direction of the surface that the point is on, and then we push the beginning and end points in the opposite direction of the normal. So basically, make them go inside of the mesh. Yeah, so let's do that. So what I'm gonna do is, I guess first I'm gonna get a normal and get our collision mesh. Then I'm gonna resample the splines that we have, just to give them a bit more points to work with. So maybe let's go for 0.5. Yeah, a 0.05. Then to sample the normals, I'm gonna get an attribute transfer, plug in my splines in the left input, the collision mesh into the right input. And let's see. It's a lot of normals. It's a bit hard to tell what exactly is going on, but if you look at some more isolated spots, we can see that the normals are basically pointing away from the surface. So I think it is doing what it's supposed to do. I don't care so much about the middle of the splines, I only care about the endpoints because these are the ones I want to move. So as long as the endpoints look alright, I am happy. Now I'm gonna get an attribute wrangle, and what I want to do now is that I want to push the endpoints in the opposite direction of the normal. So in previous tutorials, I've shown a way where we have used the group by range node. Actually, we're using it up here, where by using the group by range node, we can find the endpoints. But I thought I'd also show you how to do that with Vex. A way that we can find out if something is an endpoint along a spline is by checking its neighbor count. So what is a neighbor? A neighbor basically just means that when points are along a connected surface, for instance, a spline, that means that this point over here would have one neighbor in this direction. But this point here has one neighbor to the left and one neighbor to the right, so it has two neighbors. So basically all these points that are not at the ends have two neighbors, or more if they are at an intersection. But basically the way that we can define an endpoint is by saying you have only one point. Okay, so how do we get these neighbors? First I'm gonna set a variable called NBS for neighbors, and we are going to use the neighbor count function, and that's how you get it. We just have to supply a geometry and the point number. So yeah, so we just say 0 because we want to check this geometry, the one that we're currently looking at, and then we say add ptnum. As usual, if you want to check if something is working while you're coding, a good way to do that is by turning our variable into an attribute. So I at NBS equals NBS. Okay, so, and then I'm gonna open up the spreadsheet and let's see. Yep, here we go. We can see that we have varying numbers of neighbor counts, and it's also numbers that we would expect. So either 2 or 1, right? It should never be 0 or something, and because we don't have any intersections, it should maximum be 2. So it looks like this is working. So I'm just going to remove that again. And so what I want to do now is that based on this neighbor count, I can now set some rules. So for instance, I could use an if statement to determine whether something should happen or not. So I'm going to write if, and then these little brackets. And in these brackets is where we're going to say if this happens. And then what we need after it is we need these curly brackets. And then in these curly brackets, we are gonna say, then this should happen. Okay, so I'm gonna say if NBS equals 1, then at P should be at P minus at N, because we want the opposite of the normals, and then multiply it. And then we can add a parameter that, like a slider that we can play with. So I'm gonna say CHF hook depth. Okay, and let's see, so I'm gonna spawn this slider, and then, yeah, I think this looks like it's working. Let's check out the other ones. Okay, it's looking like in some places it's doing what it's supposed to do, but not in others. Like here it's doing the opposite of what I wanted. And after some testing and trial and error, I noticed that it behaves a bit more reliably if we change the normals into point normals instead of vertices. So I'm just gonna go to the attribute transfer, change that to point normals. And if I go back, yeah, now it looks correct everywhere. All right. Yeah, especially here we can see this nicely. What we can do then is to, just to make it a bit smoother again, is that we can get another resample node and just maybe add even more resolution, and we can change it from a straight edge to a subdivision curve. And now we get like nicely rounded off ends so that it doesn't look too, too robotic or something, but more like some organism or some plant trying to like bore its way into the surface. One thing I want to avoid though is you can see that there is a ton of points here, and as soon as I'm going to turn this into geometry, that's going to mean that, well, basically every point on our spline is going to be a multiplier for our polygons. So I think every step on the way we should try to optimize as much as we can, not only because the more we optimize, the faster it is for our PC, but also looking at it from the other side, where the more we optimize, the more of the flesh we can use for the same price, right? Let me show you a cool way how we can optimize before we even turn this into a mesh. So there's a really cool node from SideFX Labs called Dissolve Flat Edges. And this is really cool for optimizing splines, because what it does is it's analyzing the angles on our meshes, and it's removing any points that don't contribute to the shape. And you can see that it really leaves all the parts alone where we are contributing to the shape, but then anything, as soon as there's a certain flat angle, it's going to remove it. And so we went from 24,000 points to 8,000 points. And that's just for free, right? Because no one's going to notice the difference of the points being there or not being there. Okay, so now let's add some thickness to it, and we can just go back to our flesh clusters and we can just copy this whole part, the orientation along curve, the normalizing float, because we copied this p-scale code from right here where we are sampling the volume to determine our p-scale. So let's just get all of this, and of course the sweep node where we have the nice thickness fall off. Alright, so let's just paste that over here and see what comes out. And nothing, because we have this parameter in here. So I'm just gonna delete the channel again. Okay, yeah. Nice. Okay, some parts are a bit thick, and we can see about that. We can tweak the attribute normalized float, but I think overall it's doing a pretty amazing job dealing with all of this stuff. And because we were on the topic of optimization, I would also want to make sure that we don't use too much detail on our end caps. So I don't know, maybe 1 is enough, probably, or I don't know, 2. Yeah, fine, let's go with 2. And for our columns, even just something like removing one of these columns, it's just about these little tweaks, you know, that is gonna contribute a lot down the line. So now this bunch of splines is just 70,000. I mean, just 70,000. But you know, for Unreal terms, 70,000 is pretty decent. We're almost done. All that's really left to do is to add that vertex color tag back in, and we can also just steal that from our flesh clusters. So let's see where they are. So let's just go over here, there. Oh yeah, the color node also. Let's just copy that. Go back to our flesh webs. I'm gonna paste that here. And okay, we have that, we have the thickness and distance to nearest. I'm gonna connect that with our divide node. Okay. Blue random noise. Yeah, looks okay. Yeah, that's kind of it. And now we just have to turn it into an HDA and wire up the parameters. So I'm just gonna turn that into a subnet, right click, create digital asset, GROT flesh webs. I'm just gonna say create. So in the flesh clusters, it was a bit easier naming our input labels because it was very clear that one was a curve input and the other one was a world input. However, in this case, we would have 2 world inputs and would be kind of confusing to name both of them world input, right? So what's cool about this little trick that I've shown earlier, where if the term world is present in our input name, that it's going to be turned into a world input, is that it doesn't matter where the word world is. For instance, we could just call it influence mesh and then add parentheses and say world input. This would already qualify to turn this into a world input. And then I could say collision mesh and then, you know, say again world input. I mean, I could also just say world and it would work. Just trying to show that we can still have this nice little handy feature, but we can of course give it whatever name we want. All that matters is that the word world, curve, or geometry is present. And then for the parameters, I'm just gonna take a bunch that, you know, makes sense. That should be good. Oh yeah, another thing we can do for our collision input is because we don't know what kind of input we're going to be getting, right? It could be anything from, it could be a blockout mesh, it could be a fully detailed mesh, it could be a bunch of instances. So there could be a whole lot of different information present on these meshes. And just to make sure that this isn't an avenue for, you know, our tool failing or behaving unexpectedly, what we can do is we can get an attribute delete node and just delete everything except the points. So no matter what comes in, we have a cleaned up geometry because we only care about the the surfaces, and then to make sure that if these are instances, for instance in our cave, we might have instanced rocks all over the place, and we don't want to check that every time we use our tools. So let's just pack an unpack node here, and it's going to give a warning if there is nothing packed, but it's still going to let the geometry pass. But in case there were packed primitives in there, it would unpack it and then it would behave as we would expect. Alright, and one more thing that we can do to polish our tool a little bit is to work on the scatter and the connect adjacent pieces nodes. So for instance, a feature that the connect adjacent pieces node has is the cone angle. And what that defines is that based on the normals on our points, there's a certain angle that the connect adjacent pieces node is going to prefer over points that are outside of that cone. And because we don't have any normals present right now, this feature is not going to work. So I'm just going to add some normals. And if we take a look, we can see that we do have a slight difference. So for instance, we can see that we have fewer splines on the inside if I enable it, because they're gonna look in a cone around these normals that we have present. So not only is that gonna add nicer looking curves, but it's also gonna lead to a smaller failure rate, and by failure I mean intersections. So if you look at the end result, we can see that if I have the normals enabled, that we have way more curves in our end result because we are producing higher quality outputs in the first place. So this is an easy and effective way that we can create even nicer flesh splines. While we're on the topic of the connect adjacent pieces node, until this point I've mostly shown you how to get more flesh by increasing the density of our scatter node. But what we can also do is, instead of brute force just increasing the number of points, we can use the already existing points and simply allow the tool to have more connections for each point. With max connections I can say 2, and now we get a way fuller end result because each point is allowed to connect to 2 different points. And you can go higher than that if you want to, but again, be careful. Use this at your own discretion. And maybe one last way that we can affect the way that the flesh is being created is by affecting the scatter points themselves. So what we could do, for instance, is that we could remove some of them based on a noise pattern, or we could manipulate the mask attribute itself. So let's take a look. So if I'm getting an attribute noise, and I'm gonna type in mask and then change it to a float. Let's see, so I guess we would want to multiply it with maybe a min and max value. And then, yeah, so we could have this still that in general, the center is pretty strong, but then the further we go outside, the more, the more of this organic kind of randomness starts to be introduced. Let's see. Yeah, so we can immediately see that it changes from this very homogeneous pattern to something a bit more messy. I mean, of course, it also means that we're going to lose some of them. But the reason why I want to do that is because of these scenarios where we have a very large area, maybe, like the ruins themselves, which is just this big slab of concrete, and I want to avoid that we have this very perfect, clearly visible cutoff radius where the flesh stops growing. Yeah, so maybe let's try something like that. And let's get back to Unreal. Alright, so before we go to the actual Project GROT scene, I just wanted to show it in this simple test level. And yeah, so I'm just gonna get my flesh webs. I'm gonna get my influence mesh and my world input. So I'm just gonna get these walls and these cubes. And we can immediately see that it's starting to affect the environment, and that it works even with super low poly geometry, because if we look at the wireframe, we can see that these walls are actually just cubes that are stretched really, really far. If I now start to move this cube, we can see how the Flash starts to try and connect these two together. And now let's check out the parameters. So I can, for instance, increase the range of this effect. And if I start to move around my influence mesh, it's also going to start affecting where this Flash is going to grow on. And we don't need to have the sphere visible, by the way. We can hide it and just play with the gizmo. Yeah, and the cool thing is that we can just play around with the meshes and everything will adapt. So if I move this here and I start moving the cube around, as long as it's still in that range of my influence mesh, it's gonna work just fine. And if I want to include these cubes over here, all I have to do is just go back to my world input and just add these. And as soon as they enter the range, they're gonna start being affected. So I feel like the wall is getting a bit too much love compared to these other cubes. So what I can do is I can go back to my sphere and just move it a bit away from the wall and a bit closer to these guys. So that's what I think is the beauty about this Flash Webs tool. It's incredibly simple in its logic, but the simple logic can very quickly create very complex looking end results just by playing around with it a little bit. And it shows also how it's not only up to the tool to come up with something awesome looking, it's also up to the input to define what there even is to play with. But yeah, so I think that makes it clear how this tool is operating. So now let's check it out in our actual scene. All right, here we are in our GROT scene. And as you can see, we have our Flash already in place on our ruins, and all that's left to do is just to fill in these gaps. It would be cool if around the entrance there was just this nice little layer of these flesh cobwebs, you know, like on these rockified people, in these crevices, just to kind of give this impression of this flesh that's almost spilling out of these ruins. We don't know what's in there, right? It might be some, I don't know, some evil mage or something, or some monster, or just some demonic energy. So I'm just gonna drop my flesh webs into the scene, and I'm gonna get a sphere. I'm gonna start with this general area here around the entrance, something like this. Let's get the influence mesh. Then I'm gonna get my ruins, my flesh clusters, my rockified people, some more rocks. All right, let's see what happens. All right, so it's all pretty colorful and messy, but let's take a look. Yeah, I mean, what's pretty cool about these webs is that you can see that they even interact with the flesh clusters that exist already. And we can go one step further. So for instance, if I get my ruins flesh and I drop that in the flesh material slot, we can see that they are now also, because they share the shader, we can see that they're also now pulsating in unison. And what's even cooler is that you might have noticed that we have supplied an HDA as our input. And so if we wanted to, we could actually move these rocks around, and then the output would be fed to our flesh webs, and then they would automatically be recalculated. If we wanted to, we could hook up all these three tools in this layered manner where we have the ruins tool, and when we make a change to the ruins tool, the change is going to be passed on to the flesh clusters, and as the flesh clusters change, the change is going to get passed on to the flesh webs, and then we have this kind of this hierarchy of dependencies. If you want to, you can chain together several HDAs and make this fully procedural layered environment. Okay, so I think this looks really sick, but I now want some more flesh, maybe just kind of around the ruins, along these crevices where the concrete meets the rock, just to make it feel maybe, you know, a bit more connected to the environment. And I might want to use different settings for it, as I did just now. So let's just get another flesh webs. I'm gonna drop it in here, and I'm gonna get another sphere, and I'm gonna put it somewhere, yeah, somewhere here. I'm gonna get the ruins, and then maybe these two rocks and the floor. So let's have a look. I might want to adjust these a tiny bit. I think I'm gonna do a longer minimum distance, maybe less density, but I want it over a larger area, so I'm gonna maybe double the growth radius. Ooh, okay. Yeah, this might be something. Let's see what it looks like with the flesh material. Okay. Let's see, maybe I'm also gonna make it a bit thicker. Yeah. I think this is already doing a great job. I mean, just from experimenting a little bit and trying out our tools, we already made something really, really cool looking. So just imagine what you can do when you seriously put the time into it, or if I were to give this to an environment artist. Alright, that wraps up the Flesh Tool series. I hope you learned something new, had some fun, and found Houdini and proceduralism a bit more approachable. But this is just the start of your journey. What if you added veins growing from the flesh tool, or repurposed the tech to create a vine tool or a root tool? The possibilities are endless, so keep experimenting and see where your creativity takes you. Alright, have a good one, bye bye!